Hello and welcome to the talk called Observability Tools. In this talk we will talk about tools that you can use to quickly gather insight into what your program is doing and how is it behaving and why is it behaving that way that it is. So a short information about myself. So I'm Ivica Bogosavljevic. I'm an application performance engineer, and my professional focus is C and C++ application performance improvements. That means many ways how you can make your software faster. I write for a software performance blog called Johnny Software Lab, and you have a link here in the footer. So this is the link. And finally, I also work as an external expert. So if you have problems with performance in your software, feel free to contact me. So this is the email address you can use. Okay, let's start. So many people use most of the time debuggers or printfs when they interact with their programs. Now these tools are really useful, and there's no doubt about it. But they're really too coarse for some applications. Now the question is, can we do better? And the answer is yes. There are tools called observability tools. So there are quite a few of them that can help us understand what the programs are doing. So imagine that you're starting to work on unfamiliar code base and you want to understand which functions are important, which functions are less important. The typical tip is read the code, but if the code has 1 million lines, then what code should we read? Now, using observability tools, you can understand which part of the code is more important, which part is less, and how code interacts with other parts of the code in time and in many other ways. You can also get information about memory usage, so how your program uses and consumes and disposes of memory. You can understand the hardware efficiency of your program, how hardware efficient it is, how well does it work with hardware, and finally you can understand how your program interacts with the operating system. So we will cover all of this in this talk. You can also use observability tools to debug some weird or unusual behaviors. Now, during this talk, we're going to give several examples, and all the examples that we are presenting are available at this address. This is my GitHub, so you can feel free to copy the code and run it or adjust it for your own systems and your software. Most of the things, all of the tools that we present here are Linux-based tools. I guess there are some equivalent Windows-based tools, but unfortunately I don't work with Windows, so I cannot tell you exactly what they are and how you can use them. Okay, so the first tool is called Flame Graphs, and in our example we will use SpeedScope as the tool for the observability as an observability tool. So what are flame graphs? So this is a screenshot of a flame graph of some program, and actually if you analyze it from top down, you will see these are stack traces. So start calls libc main, calls transcode, calls rip filters, and so on. And so on the y-axis you have the stack traces, on the x-axis you have time. And this visualization is really useful because it can help you in several ways. So let's explore it by ourselves. Now I'm going to run the code. I'm going to run the code in the command line. We will use the examples that we already provided. So here we have several scripts. The first script, it just downloads the repository and compiles everything with good flags. And the second script, 01, is actually the running of SpeedScope. Now about the SpeedScope, the things you need to do is that SpeedScope is actually just a visualizer. It's an application that is running in the browser. To collect data, you need some kind of data input, and on Linux this is perf. So for those of you who don't know, perf is the Linux-based Linux profiler, and it can collect information about the running program. So how does it do it? It's a sampling profiler. That means occasionally it will stop the program and collect the stack traces, and you can see on the stack trace which function was calling which function. So you see this a single stack trace. Now this command actually runs this program called lulesh, and collects the data. For this example, we're going to use the Lulesh. Lulesh is a scientific a program from the scientific community, which is really small, and this is appropriate to use for this talk. So we're telling perf to record information about Lulesh, and we are telling it to take the stack trace information from the debug symbol. So this is dwarf. And finally, we tell it to perform sampling 99 times per second. So when this command is done, we will get the perf.data file, which contains the profiling information. This command parses the perf.data file and feeds it to SpeedScope. Okay, so let's start. Okay, now the program has finished executing. It took 70 seconds. And now it is processing the collected data and converting it so SpeedScope can actually use them. Okay, so this is SpeedScope. Just a second, please. Okay, so we have here the SpeedScope screen. We just try to zoom in a bit. Yeah, that's better. Okay, so this is the SpeedScope window, and here we have all the threads in our program. In this case, Lulesh had only one thread, and the perf exec was the second thread, and we are not interested in perf exec, so click Lulesh, and here we get this kind of graph, but it's all looks like garbage, but actually it's not. So let's explain what are the options to SpeedScope. There are three options, three ways of displaying data. One is called time order, the second is called left heavy, and the third one is called sandwich. So currently we're in the time order. So if you imagine this code, on the y-axis you have stack traces, on the x-axis you have time, and this code took about 90 seconds to execute. Now, the time order will tell you how your program was actually executing, which functions were called, how it went from one function to another as a function of time, so as the time was progressing. Now, to get actual usefulness from time order, you need to zoom in a bit or zoom out. So if you zoom in a bit now, the things becomes a little more clear. So our program was actually working like this. So there was a main which was active for the whole time, and inside there is a function called Lagrange leapfrog, and from that there is Lagrange nodal and Lagrange elements. Lagrange nodal, Lagrange elements, Lagrange nodal, Lagrange elements. Now if you go down the call stack, you can see that Lagrange nodal was calling calc force for nodes, which was calling calc volume force for elements, and so on. So if you move it, you zoom it and then move it left and right, you can see how the program was behaving, how it was moving from one function to another, so how it was executing, what was the function flow and data flow for the program. Okay, so we see here that most of the time it was most of the time calling these two functions, except for at the beginning when the dynamic linker was doing its own magic here, as you can see. So if you go up to down, you see the stack trace. You go left to right, you see time. The next view, it's called the left heavy view. So I'm going to click it. Now, left heavy and time order look quite similar, but they actually have completely different intent. In time order, you see how the program is going in time. Left heavy doesn't do that. So with left heavy, you can see how much. It's a cumulative view, which can tell you how much time was spent in each function. So the program was running for 90 seconds, and 1.08 seconds was spent in Lagrange leapfrog. So it puts the left heavy, the most heavy stack traces on the left and the lightest on the right. So that makes it good to investigate where your program is spending a lot of time. You see that about 51% of the time was spent in Lagrange nodal, and about 47% of the time was spent in Lagrange elements. And you can see which functions were actually consuming time. And this view is actually useful when you want to understand where your program is spending time. Also, the first time order view tells you how the program is moving from one function to another function. This tells you where it was spending time. So this is the key question this view is trying to answer. The last view is called sandwich. And what's this? So sandwich actually is a list where the function names are sorted by runtime. Now there are two columns. One is called the total and the second one is called self. Total time means the time that the function was executing either itself or its children function, the function it called. Self is only calculates the time, only counts the time the function was on top of the stack, so it was executing itself. And if you look at this, if you look at this, you see that the CalCaf B hourglass force was spent 14.62 seconds total. And out of these 14 seconds, 12 seconds it was executing its own code. That means that 2 other seconds it was executing other functions that it was calling. Now, if you, for example, if you're interested in improving the performance of your code, you would sort this table according to self, and then you will start investigating the functions that take the most time. So in this case, it's CalCaf B hourglass force for LM. The tool is actually really useful. It works as advertised, so you can get more information about it on this site, speedscope.app. You can get more information on how to collect data using perf here. And the good thing is that SpeedScope supports many languages and many profilers, including Windows profilers. So you can check out the documentation and see how it goes. So next topic are heap profilers, and example of one such profiler is called the heap track. So what is a heap profiler? Heap profiler takes your program and hooks into the allocate and deallocate, malloc, renew, delete, whatever, and then it can measure how much. It can tell you a lot of things about your memory, how much memory was spent by your program, where it was spending it, which were the functions that allocated the most memory, and so on. So it is good for debugging memory consumption issues, and it also can tell you. It can also tell you if your program is, for example, memory intensive, that it is, although it's not consuming a lot of memory, it is making a lot of calls to the system allocator, making a lot of calls to renew and delete. Okay, so let's see the example. Here I prepared. So I'm gonna print out the. So heap track is installed from the Linux repositories. It is a really nice tool, visualizer. It works really well. So this is how it works. You just call heap track and the name of your program, and it will record information about how your program is working with the memory, and it will store this information to a file. In the next line, we use heap track -- analyze to analyze and visualize the information that the heap track collected. So let's give it a try. So we call dash 02. Okay, and this is done. So if you see here the heap track screen. And this is the summary screen, and we can see what are the peak contributions, so where most memory was allocated, even the location, see. And so what were the functions that allocated most memory, what were the largest memory leaks, so it detects also memory leaks, where most allocation done, so this allocate double, and what were the most temporary allocation. Temporary allocations are allocations that you make, you call new, you get your memory buffer, you use it, and you dispose it without calling any other new and delete in between. So these are called temporary because normally you can replace them with stack allocations. It would make completely sense. So here is the bottom-up view. We see here that the double allocate was called by several other functions. Eval EOS for elements, domain allocate strains, calc energy for elements, and so on. And we can see which of the calls actually make the most allocations, both in terms of memory and in terms of allocation count. There is also a caller callee, so you click on a line and it will tell you who was the caller of that line and who were the callees of that line and where most allocation was actually done. There is also top-down approach. So these are things that are familiar to most developers. Flame graphs that we talked about. So we see here as a flame graph, and you see that about more than 54.4% was allocated in this double allocate double function. We see here the consumed graphs. This is interesting. So the consumed graphs tell you, it will tell you, you see that the program was allocating around 19 megabytes of memory. So we see how the memory consumption was growing and how it was falling as a function of time. So the x-axis is time, and the y-axis is the memory in megabytes. And we see here at some point the memory consumption was growing and was falling and so on. There is also these allocations. Now, in the consume section, you can see the peak memory used by a program, which is 19 megabytes. In the allocation section, you can actually see only the amount of memory requested from the allocator, not deleted. So you can see how the memory, memory intensive is your program, how many calls does it perform on the system allocator, and you see that it grows to about, the program during its lifetime does almost 200,000 allocations. So these are really nice things that you can use heap track for to see just to understand how your program is actually interfacing with the system allocator. So the next tool we have in our toolbox, observability toolbox, is the coverage tool. So example, if lcov, which is available on Linux. So you see here the coverage tool output. Again, it's a visualization tool. So for each line in your source code, it will tell you how many times that line was executed. So we see here that this line was executed 24,325 times, and the other line was executed only 838,000 times, and so on. So why is this useful? If you have a function and you're looking at it and you want to see which parts of the functions are more important and which part of the functions are less important, then coverage tools are really good thing to use. So an important notice about coverage tools is that they work a bit differently compared to the previous two tools we mentioned. For the coverage tools to use, you need to compile your program with this -- coverage option, compiler option, and because this compiler option will be sent to the compiler. So let's have a look at the. Just a second, please. So let's have a look at the source code, how we use the coverage tools. So we need to build the lulesh, our example lulesh, with the / coverage option, and then we execute lulesh, and the output is a coverage file, so it will tell you which line was executed how many times. So the compiler is the one that actually putting information about which lines were executed how many times. Then we use this, so this tool will collect several coverage files and create one coverage file, and then we use this gen HTML to generate HTML report, and in this line we open the report. So let's run it. So I'm quite sure there are coverage tools also for in Windows and also visualizers on Windows, although I myself don't use Windows. So all of the tools that we were presenting here actually exist on Windows as well. Now, one of the things that happen is that when you build your program with the coverage option, you should expect some slowdowns because the compiler is actually adding new code as part of your old code, which counts how many times each line or basic block was actually executed. So the runtime is typically somewhat slower. Okay, and here we have it. So this is the report produced by LCOV, so the code coverage report. And now we are, for example, interested in the directory Lulesh. I'll click here, and I will see the Lulesh CC file name. And again, here we see the Lulesh source code, and for each line we see how many times it was executed. And now, normally if the function doesn't have any if or for, we are not that interested. But let's have a look at what happens here. So if you look at it like this, so if this line was executed 1,864 times, and this was executed 50,329,864 times, then you can actually estimate the number of iterations on average for this loop by dividing these two numbers together. Also, if you look up if statement, then you will see that you can understand how much time the if branch was executed, how many times the else branch was executed, and we see that this condition was almost always true, but this condition was almost always false, because although it was evaluated 1,862 times, it was actually executed only 16 times. So this is a really nice information to have about your program. Next observability tool that we're going to talk to you about is called the kernel system call tracers or kernel call traces. And in our example, we're going to use strace. So a few information about strace. So first, what are system calls? System calls when your program needs some favor from the operating system. For example, it wants to read a file, write a file. It wants to sleep on a mutex. It wants to allocate memory. It wants to send or receive data over network. So this is the things that typically the program cannot achieve by itself. So it needs to ask a service from the operating system through system calls. Now, some programs do a lot of. Some programs they make a lot of system calls, other not so much, and it will really depend on the type of the program that is running. So in case you notice that your program is behaving weirdly, or you want to see how your program is actually working with the operating system call tracing or strace or any other system call tracer is actually a good tool to have and good tool to use. Now, in order to understand what your program is doing, you need to understand which system calls is it making. Now, there are many system calls, but most programs just use a few dozens. For example, read, write, open, close are system calls related to working with file. Mutex is related with mutexes. BRK, munmap, and mmap are related to memory management. And you see here that this BRK is called many times. Also, there are stat and fstat, which you can use to read information. For example, you want to know the file size, the directory number of items in a directory, or the contents of the directory, then you will use this system calls, and so on. So When you investigate your program, you can always look up system calls online, so this information is readily available. Okay, so let me just show you how it works. Strace is in this. So if you want to execute, if you want to run your program with strace, you just provide strace and the file name. So if you see here correctly, I'm redirecting this to a file because the file can, the output of strace can be really, really large. Another option that is available is strace-c, where you are displaying cumulative information about system calls. So this one will print every system call that the program is making, and this one will not print anything until the program is done. And when it's done, it prints how the amount of time, percentage of time that the program has spent in system calls. So there is also this K option, and K option means that not only the system call and its parameters will be displayed, but also there will be a backtrace. So what line actually made the system call, and this can also be useful if you're debugging system calls. So let's run it. Bash 04 strace. Now strace also will make your program slower, and how much slower actually depends on the program itself. If it's not making a lot of system calls, it will be a bit slower, but if it is making a lot of system calls, then it can be much, much slower. So let's wait and see what happens here. Okay, I had to interrupt this because it was taking too much time, but if you look at this here, you see that 72% of the time was spent in the Futex system call, and 27% of the time was spent in the BRT system call. So a lot of time was spent actually in the Futex system call, and the reason why this so is because this program was actually running 8 threads, so there was some synchronization involved and some time was spent there. So let me just show you. So I had to interrupt this because it took too much time, but let me show you the strace example where you can see individual traces. So this is the cumulative display with -c, and there is also a possibility to display something like this. So this won't work because there was an error. But if I write /build and I look it like this, so we're gonna just run a few seconds, 1, 2, 3, 4, 5, okay, because I want to show you what's inside. So here is what strace actually collected. So there is a lot of information here, but if you look at it like this, this is a system call called openat. It gives the file name and some information. So it is trying to open this libstdc++ at this directory, but it's not working, so it's moving on to another, trying to open the same another directory and so on. So you can see here everything that the program is actually doing. So in this case, the dynamic linker is trying to open the libraries needed to run Lulesh, and so you can investigate which are the directories that the program is accessing. You can also see the memory allocated and all sorts of things. Now I know a guy who he wrote on Linux, the cp command doesn't have a progress bar, and he used strace, so he used some kind of system call tracing and used the cp command, and then the read. So when cp is reading files, it is using the read call, and read call has also the number of bytes. So this guy he was checking how much data the program was actually read, and it was displaying a progress bar depending on the amount of data that the program was actually read. So this is a really good approach of how you can use system calls. You can also, for example, spy on programs and see what kind of data it is exchanging with the other parts, with the outer world, by spying on send and receive system calls used for networking. The last tool we're going to talk about in this talk, it's called perf. So the perf will tell you, perf is a Linux profiler. It's available on Linux, and it can tell you various information about your program. And here we'll only limit ourselves to the most important information. So if you run perf, so you will get a few important information. So what is the most important here? First, if you look at here, it will tell you how much time did your program take. This is 0.94 seconds. And here you will see that the program spent 0.93 seconds in the user mode and 0.016 in the system mode. So user mode is actually what your program was doing, and system mode was how much time did the program how much time did the operating system was doing work for your program. So this is really important, and related to the previous talk about test trace, we see here that program doesn't spend a lot of time in the system mode, so it's probably not a good idea to. I mean, if you're interested in performance and you want to make it faster, then S-trace is probably not the place where the problems is. The problem is in the user code. Okay, if you look at this graph here, you will also see that the amount of cycles. So here we have this really large number. The amount of instructions. So, and the third one is instruction per cycle. So cycles is the CPU cycles, how much it spent, and it corresponds to time. More cycles means more time. Instructions is how much instructions has the CPU executed, and this correlates with time, but sometimes you can have programs which have more instructions and actually take less cycles. And here we introduce this metric called instruction per cycle, which measures hardware efficiency. Now, modern Intel and AMD CPUs can execute at most 4 instructions per cycle, so this is a theoretical upper limit, but you will rarely see this. But the program that's executing more than 2 instructions per cycles would be considered quite hardware efficient. Not efficient program would execute less than 1 instruction per cycle. Okay, let's look at the command line again. So this is the perfstat. And if you see here, we have to run your program using perfstat, you just type perfstat and the name of your program. So for this example, we're going to investigate this matrix multiplication example. So we are moving away from Lulesh to matrix multiplication, and I'm going to show you the source code and explain what's the problem here. So here is the matrix multiplication hot loop. So this is the biggest loop. And this is a textbook implementation of matrix multiplication. We have 3 nested loops, and we have three matrices A, B, and C, and we calculate say if C of ij equals C of ij plus A of ik times B of kj. Okay. So we have 2 implementation. The first one has ijk, so 3 nested loops are ijk. And the second one, called multiply mul2, also has 3 nested loops, but this time they're I, K, J. So what happened is that I exchanged the innermost loop over K and the middle loop over J. So I exchanged them, I moved them up. The one that was previously inner became the outer, and so on. So quite simple modification. Now let's run our program with this and see what happens. So I'm gonna bash perfstat. So this is running an example on matrix size which is 1200, and so it is doing multiplying large matrices. Okay, so let's see what happened. The first program took 8 seconds to execute, and the second program took 3 seconds to execute. So the second program was almost 2 times faster, more than 2 times faster actually. If you look at the cycles, this program took 154 and this program took 57. So you see that the cycles actually do correspond with the time, because this is the proportion between times. In terms of instruction, the first program took 140 and the second program took 71. So it executed almost 2 times less instructions compared to the original program. And you see here also the efficiency. We have in the first program 0.91 and in the second is 1.23. So the two things are obvious. The second program executed 2 times less instructions, and it was actually higher hardware efficiency. Now what has happened? Let me explain you what has happened. So let's open the source code again. So we have these 3 nested loops. So let's observe what happens when k increases by 1. So when k increases by 1, access to C of ij remains constant. That means that this variable can be put in register because it doesn't change. It is a constant. When k increases by 1, we are accessing the next value in the same row. So we are accessing next value in the same row. So we are going through this matrix A row-wise. So row, then next row, then next row, then next row, and so on. And lastly, what happens when k increases by 1? So when k increases by 1, we are moving to the next the same column. Same row, just next column. So we're going through the matrix down, 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 down. So we are skipping the whole row, and we are just skipping rows, the whole rows, and they're just moving down, down, down. So since we know that matrices are stored in C and C++ row-wise, so this access is actually like accessing array. We're going from 0, 1, 2, 3, 4, 5. And this access here is like we are again accessing an array, but we are jumping over n elements. So because this is the size of dimension, so we n element jumping. We call this access constant. This is sequential access, and this is strided access with stride, which is n. What happens if we exchange the outer, middle, and the inner loop? Let's do analysis again here. So if we exchange it now, what we're actually interested in is what happens when j increases by 1. So if when j increases by 1, we get a sequential access for C. So we are accessing elements sequentially. When j increases by 1, nothing happens for A, so it's a constant access. We're also always pinning the same memory address. And finally, here we have what happens when the j increases by 1 is that the access to B is also sequential. So here we have 2 sequential and 1 constant access, and originally had constant, sequential, and strided access. Now what happens is that when you have a strided access, strided accesses are much less memory efficient compared to sequential accesses. And that's why we see that the program is much more memory efficient. Now that explains the difference in cycles, but doesn't explain the difference in instruction size, in the instruction count. This example has 2 times less instructions than original example. So what actually happens is that compiler, seeing that all the accesses in the innermost loops are either sequential or constant, decided to automatically vectorize the loop. So what is vectorization? So instead of doing one instruction, in simple scalar, one instruction works with one piece of data. So it works with one double. It loads one double, it adds two doubles, and creates a third one. It stores one double to the memory. Vectorized code, on the other hand, works with more than one pieces of data. For example, with 4 or with 2. So it can load 2 doubles from the memory to the CPU. It can perform two addition with one instruction performs two addition, with one instruction it stores two pieces of data back to the main memory. And this explains the difference in instruction count. All modern CPUs, desktop and server support vectorized code. Okay, so the last thing is, this is the end of the talk about the observability tools. I hope you had fun. Now the question is there anything missing? And actually there is. So the things that are missing here, one of the important things that I think that it's missing here is called the data flow analysis. And the one and only tool that can actually do it is called Pernosco. Now, what is data flow analysis? Imagine you are debugging your program and you see that in some variable you see a wrong value. Now you're trying to establish where this value comes from. What is the chain of events that led to this wrong value? With data flow analysis, you run the Pernosco debugger and it generates this web interface. Then you click on your bad variable, on the bad value, and you see exactly which lines in code actually caused this bad value. How come did this bad value propagate here? Now, I thought this was science fiction, but it's actually something that works, and I suggest to everyone to visit Pernosco website and see how it works. What I also didn't cover here are the debugging tools, and I think they're also really important for each developers. So Valgrind, Valgrind and sanitizers and Valgrind are used to debug memory corruptions, stack corruptions, heap corruption, that stuff. Hellgrind is used to detect thread races, so where you have two threads accessing the same data simultaneously. Another tool that I really like is Reverse Debugger, RR, and reverse debugging allows you to run your program backwards. So you have step, but you have reverse step. You have next, but you have reverse next. You can put a breakpoint on some code and then reverse run it until the breakpoint is hit. So this is really useful when you are trying to establish what causes the problem, because the cause is somewhere in the past. Next thing that is also important is programming for observability and for debugability. So if you have your program, you should strive to program for observability. So what does that mean actually in practice? One thing, for example, are counters. So imagine your program is producing some kind of data, like say messages sending to other parts of the system. You want to count the number of messages produced per unit of time, for example, so you can see peaks in memory production which can indicate some problems. You can use so for this case you would use counters. You would count and then you can visualize this information and see peaks consumed and so on, similar to the heap profiler that we were explaining today. And the last thing that also is quite useful in my experience is data flow debug IDs. So what are these? Imagine you have your data that is going through several pipelines, so several threads that are doing some processing on those data, and at some point you see some kind of error. Now, what would you actually do is when your data is produced, you save some kind of ID and you preserve this ID during the processing of your data as much as possible. So when the error happened, by looking at the ID, you can pinpoint the exact place where it happened.